Welcome back, everyone, to part 2 of lecture 3 for MAE 170. So we're going to start this part 2 talking about a very important concept in control systems, which is known as the transfer function. Remember that so far we've been considering uncontrolled systems. That is, we just simply have a process in our black box over here. We feed an input to the process, and we're going to see its output. The transfer function, in a few words, just describes the nature of the process, and it is given as a function in the S domain, which we're going to call it g of s. All right, so it has many meanings, the concept of transfer function. Let's just explore a few. So as I said, first of all, the transfer function describes the dynamical property of a process or of a system. If we take a more complex system, we can reduce it to just input, black box, and output. And the function describing the characteristics of the black box is still a transfer function. We can also mathematically define it as the ratio between the output and the input. However, this has to be done when the initial conditions are all set to 0. And why is that? Well, so that g of s will depend only on the system parameters. And it will not depend on the particular initial conditions. So if we just assume that the initial conditions are equal to 0, we can find a consistent function, that is g of s, that depends exclusively on the system and on the system parameters. And being just a characteristic of the system, in this case of just the process, because we don't really have a control, well, g of s itself is independent of the input because, well, we can feed the process a certain input and it will give us an output. But if we change the input, we will have a different output. But g of s itself, the ratio, will always be the same. And okay, that's what I wrote here. It's the ratio between output and input for 0 initial conditions. This is always in the S domain. It's very easy in the S domain because we can simply use the ratio. In the time domain, it would be way more difficult, involving convolution integrals in order to define the transfer function. So the S domain is the way to go. Since g of s is equal to y over r, well, and if r is simply 1, then g of s is equal to y of s, or in other words, the transfer function is equal to the output when the input is an impulse. Let me just prove it to you. If the input is an impulse, that is the Dirac function or delta t, in the S domain, r of s is transformed into simply 1. So y of s, that is the output, is equal to the transfer function of the process times the input. But since the input is simply 1, well, then the output is equal to the transfer function. Or in other words, the transfer function is equal to the output when the input is an impulse. Another property of transfer functions is that they convert units, but they do not necessarily say anything about the physical nature of the system. If I give you a transfer function g of s, it's just going to be a function of s, it's just a fraction. And you don't really know, if I don't give you more details, anything else about the system. And as I also said, it can convert units. Think about the example of the mass damper spring. The output is the position. The position of the mass is measured in meters. And the input, as for how we define the system, was the external force. So, of course, the external force is measured in newtons. So the transfer function converts newtons to meters in this case, but it can also be dimensionless if the output and the input are the same. For instance, if the input was a movement of the base to which the mass is attached, let's say that R of t was the movement of the base, well, then R of t would be expressed in meters as well, and Y of t, if we always assume that it indicates the position of the mass, then the transfer function will simply be dimensionless because it would convert a position into another position. As I said, it is very convenient to express things in the S domain because in the S domain, the output is simply equal to the transfer function times the input. That's as easy as that. Instead, if we were to operate in the time domain, we would have to use a convolution integral between the function, transfer function, and the input. So we would have to solve this integral, which can also be written with this star symbol that indicates the convolution operation. Or conversely, that is also equal to g of t minus tau, r of tau, d tau, whichever you want. And also here, there's an assumption that both g of t and r of t are equal to 0 for time that is less than 0. That is, everything starts at t equals 0. Another thing that I want to mention is that if we know the transfer function, well, then we can study the output by feeding the process different inputs. In fact, if we know g of s, well, we can choose different r of s, which we know, and then we can find the nature of the output. Conversely, if the transfer function is unknown, so if we have a system and we don't really know, we don't have a model, a mathematical model for the system, therefore we don't have the transfer function describing its dynamics, what we can do is that we can retrieve experimentally, we can deduce the transfer function by feeding the system known inputs and measuring the outputs. And that is because g of s, once again, is the ratio between the output and the input in the S domain. So if we know R of S, because we pick the input and we measure the output, we can retrieve the transfer function. This is a little bit more complicated than this, but this gives you the idea that the transfer function can actually be experimentally deduced. All right, let's take a look at the usual example of the mass spring damper, and let's find the transfer function for this system. Why not? So here I've already written, I've left this written because that's what we found earlier in part 1 of the lecture. But let me just recap. We found that the output, that is the response of the system, which is the position of the mass, given a certain input, and here we have the spring and the damping element. Well, it's going to be given by the sum of two terms. The first term being the free response. And the free response, as I said, depends only on the initial conditions, plus the forced response. The forced response depends exclusively on the external input, in this case, the external force applied to the mass, and does not depend on the initial conditions. So by the definition of the transfer function is the ratio between the output over the input when the initial conditions are equal to 0. So if the initial conditions are 0, well, that means that y naught is equal to y naught prime equal to 0. Therefore, the output reduces to the forced response. That is equal to the input over ms squared plus ds plus k. Now you can see that it's very easy to take the ratio between the output over the input. So in other words, we want y of s over r of s. So let me just be clear. I said that this is the ratio between the output and the input when the initial conditions are equal to 0. That is correct. Or you can simply say that this is the forced output over the input, whichever expression you prefer. Those two are equivalent. So in the case of just a process, so here we don't have any controller. Our process is MKD. We're going to use G of S to symbolize the transfer function. So in this case, this is equal to 1 over ms squared plus ds plus k. So this is the system transfer function, as easy as that. As you see, it depends only on the parameters of the system, m, d, and k. It does not depend on the input. You won't see r. And it does not depend on the initial conditions because the initial conditions were set to 0. Now, there's one thing that it is normally done when we're dealing with second order system, and in particular, mass damping spring systems, and that is we introduce two different quantities called the natural frequency and the damping ratio. So we are going to divide both the numerator and the denominator of the transfer function by m. So we're going to have 1 over m at the numerator and s squared plus d over m times s plus k over m at the denominator. Also, what I'm going to do, I'm going to write the numerator as 1 over k times k over m. Nothing has changed. And the denominator, we're going to write it as s squared plus 2 square root of k over m times d over 2 square root of k times m. If you take the product, this you'll go back to d over m. So I haven't changed much. Times s, or I haven't changed anything actually. It's equivalent. Plus k over m. Now what we're going to do, we're going to define omega n as square root of k over m. And we're going to call this natural frequency. And this natural frequency for physically realizable systems is always positive. And then we're going to take this Greek symbol called zeta, and we're going to define it as d over, so this is actually a definition. So it's column equal. D over 2 times square root of k times m. And we're going to call this the damping ratio, not the damping coefficient, but the damping ratio. And this ratio is always greater or equal to 0. Natural frequency is measured in radians per second, and the damping ratio has no units. It's just dimensionless. So using this definition, we can rewrite the transfer function, and this becomes just 1 over k times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. This is very important because we're gonna use this so often that you might as well learn it. You'll learn it because you're gonna use it so much. You see that this is a transfer function of a system that is a second order, because how do you know it's a second order? Because the order of the polynomial, the degree of the polynomial at the denominator, sorry, is 2. Often, although earlier I said that the transfer function allows you to convert units, but often you want a transfer function that is dimensionless. So the ratio doesn't have any dimensions. In this case, there's this 1 over k that retains some dimensions. So in the case of the mass spring damper, we've started with y over r. So as I said earlier, y is the position measured in meters, and r is the force measured in newtons for the specific example. And so we have, as I just wrote, 1 over k times omega n squared over s squared plus 2 zeta omega n s plus omega n squared. Now, if we multiplied both sides by k, we would have k y over r of s. And so your dimensionless transfer function would just be omega n squared over s squared plus 2 zeta omega n s plus omega n squared. So in this case, there's no unit because everything cancels out. And this is very often found as the general form for a transfer function depicting a second order system. Again, as I said, the order is the degree of the polynomial at the denominator. Another couple of things about transfer functions is that for physically meaningful systems, so for systems that describe something physical that makes sense, g of s is always a proper fraction. That is, the degree of the numerator is always less or equal to the degree of the denominator. And again, always going back to basic math, strictly proper function is when the degree of the numerator is just less than the degree of the denominator, not equal. So proper when you allow the equality, is strictly proper when you don't allow the equality. And also something very important is that the transfer function must be reduced to the lowest terms. And what I mean by that is the following. Let me give you an example. So if we had g of s equals s plus 1 over s squared plus 2s plus 1, one would be tempted to say, oh, this is a second order system because the degree of the denominator is 2. However, this is a first order system because we can simplify things. So if you decompose the denominator, you'll see that this is just s plus 1 squared. So s plus 1 at the numerator goes away, and g of s is simply 1 over s plus 1. Big difference. Okay, so pay attention. If you can simplify, always do that. You have to do that. You have to reduce it to the lowest terms. And only when you do that, you'll find the actual transfer function for the system. Okay, here we're going to see another numerical example, but now we are given a transfer function and the input, and we want to find the output. So we're given that the transfer function in the S domain is 1 over S plus 2, and the input is a step input, constant input. So in the S domain is 1 over S. So in the time domain, this is equivalent to having g of t equal to e to the power of minus 2t, and r of t equals u of t, or just simply 1. So I'm going to solve this in the S domain, and I'll let you do the same in the time domain, and so you can compare whether or not you'll find the same output, which you should. So I'm not going to do it step by step in the time domain, but all the steps are included in the notes. So I'll just cover the S domain. All right, so y of s, that is the output, is given by the transfer function g of s times the input. So in this case, we have 1 over s plus 2 times 1 over s. So it's 1 over s times s plus 2. Okay, that's it. We have y of s in the S domain. Let's do a little bit more and let's find the output in the time domain. So what do we have to do? We have to apply the partial fraction expansion that we saw in part 1 of the lecture. So what are the roots of the polynomial at the denominator? Well, the first one is 0 and the second one is minus 2. Very easy to spot in this case. So we can write a over s plus b over s plus 2. 0 and minus 2 are obviously different roots. I'll let you do the intermediate steps, and you can see that you'll find that a is equal to 1/2 and b is equal to minus 1/2. Or y of s is equal to 1 over 2s minus 1 over 2 times s plus 2. So now when we want to go back to the time domain, we have to apply the inverse Laplace transform. And 1 over 2s is simply 1/2. It's just a constant function. And 1 over 2 times s plus 2 is 1/2 e to the power of minus 2t. Now here to the right, I've plotted the 3 functions that are the input, the transfer function, and the output. The input is just a constant equal to 1, so it just remains constant as time goes by. The transfer function is just e to the power of minus 2t, so it just goes to 0. And if you apply the convolution between r and g, you'll find y of t. Again, in the time domain, but we didn't need to do that in the S domain. So y of t is this function over here, which approaches 1/2 as time goes to infinity. Now, as I said, in the time domain, I'll give you a hint. What you need to do, you have to solve the convolution integral. So the integral between 0 and t of g, evaluated at t minus tau, and r of tau in d tau. So you can use g of t equals e to the minus 2t. So g of t minus tau is e to the minus 2 t minus tau. And r of t is 1, so r of tau is also 1. If you solve the integral, which is a quite elementary integral at that, you'll find that the output is 1/2 minus 1/2 times e to the minus 2t. So same output. And that was expected. You have to find the same thing. If you don't, it means that something is wrong. Okay, I'm gonna stop here. So I'm gonna have 3 parts because the next part is block diagrams, which is a little bit different. So again, when you go back to the videos, you can just choose to go to partial fraction expansion, transfer functions, or block diagrams. So I'll see you in part 3.